When running a rigid metal conduit from a motor control center or MCC to within 3 feet of a 480 volts 3-phase motor, and connecting the conduit to the motor using non-metallic Sealtite along with a properly sized ground wire run with the motor leads, the question arises whether a grounding jumper wire is required on the outside of the non-metallic Sealtite, or if the ground wire inside the conduit is sufficient, assuming it's properly connected on both ends. According to Article 250.118 of the National Electrical Code, or NEC, equipment grounding conductors installed inside raceways shall be permitted to be used as grounding jumpers for enclosures to which the raceway is connected. This means that the ground wire run inside the conduit can serve as the grounding jumper for the motor, provided it is properly connected to the motor enclosure and to the grounding electrode system at the MCC. The Sealtite, being a non-metallic conduit, does not provide a continuous electrical pathway for the grounding current. Therefore, a separate grounding jumper wire is not required on the outside of the Sealtite. The purpose of grounding is to provide a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices, such as circuit breakers or fuses, and minimizes the risk of electrical shock. The equipment grounding conductor, or EGC, which is the ground wire run inside the conduit, plays a crucial role in this process. It connects the non-current carrying metal parts of electrical equipment, such as the motor frame, to the grounding electrode system. When a fault occurs, such as a short circuit between a live conductor and the motor frame, the fault current flows through the EGC back to the source. This high current causes the overcurrent protective device to trip, disconnecting the circuit and preventing a dangerous voltage from being present on the motor frame. Since the Sealtite is non-metallic, it cannot serve as an equipment grounding conductor. The EGC inside the conduit is the primary means of grounding the motor. Proper connection of the EGC at both ends is essential to ensure its effectiveness. At the motor end, the EGC should be securely connected to a grounding terminal or lug on the motor frame. At the MCC end, the EGC should be connected to the grounding busbar, which is connected to the grounding electrode system. The grounding electrode system typically consists of a grounding electrode, such as a ground rod or a metal water pipe, that is buried in the earth and connected to the building's electrical service. The size of the EGC is determined by the size of the circuit conductors, as specified in the NEC. The NEC provides tables that specify the minimum size of the EGC based on the size of the ungrounded conductors. It's crucial to select the correct size EGC to ensure that it can safely carry the fault current. The type of EGC used must also be suitable for the application. Typically, insulated copper or aluminum conductors are used as EGC. The insulation color for EGC is typically green or green with a yellow stripe. The NEC also allows the use of rigid metal conduit, intermediate metal conduit, or electrical metallic tubing as EGC, provided that they are properly installed and meet certain requirements. However, since non-metallic Sealtite is being used in this case, it cannot serve as the EGC. In summary, when using non-metallic Sealtite to connect a motor to a rigid metal conduit, a separate grounding jumper wire is not required on the outside of the Sealtite, provided that the ground wire inside the conduit is properly connected at both ends and meets the requirements of the NEC. The ground wire inside the conduit serves as the equipment grounding conductor and provides the necessary path for fault current to return to the source. It is important to consult the NEC and local electrical codes for specific requirements related to grounding electrical equipment. Additionally, it is recommended to consult with a qualified electrician to ensure that the grounding system is properly installed and meets all applicable codes and standards. To further elaborate, it is beneficial to understand the different types of grounding systems. There are typically two main types of grounding systems: system grounding and equipment grounding. System grounding involves grounding the neutral point of the electrical supply transformer or generator. This provides a reference point for the voltage and helps to stabilize the voltage during normal operation. Equipment grounding, on the other hand, involves grounding the non-current carrying metal parts of electrical equipment, as discussed earlier. The equipment grounding system is designed to protect against electrical shock and to facilitate the operation of overcurrent protective devices. In the scenario presented, the focus is primarily on equipment grounding. The goal is to ensure that the motor frame and other metal parts are properly grounded to minimize the risk of electrical shock and to provide a path for fault current. The NEC provides detailed requirements for equipment grounding in Article 250. These requirements cover various aspects of equipment grounding, including the size and type of equipment grounding conductors, the methods of connecting equipment grounding conductors, and the grounding of specific types of equipment. When installing an equipment grounding system, it is important to follow the NEC requirements carefully. Failure to do so could result in a hazardous electrical condition. For example, using an undersized equipment grounding conductor could prevent the overcurrent protective device from tripping in the event of a fault. This could result in a dangerous voltage being present on the motor frame, which could pose a shock hazard. Similarly, improper connection of the equipment grounding conductor could also compromise the effectiveness of the grounding system. Therefore, it is essential to ensure that all connections are tight and secure. In addition to the NEC requirements, local electrical codes may also have specific requirements for equipment grounding. It is important to consult with the local electrical inspector to ensure that the installation meets all applicable codes and standards. Another important consideration when grounding electrical equipment is the concept of impedance. Impedance is the total opposition to current flow in an alternating current circuit. It includes both resistance and reactance. A low impedance grounding path is essential for effective grounding. A high impedance grounding path can limit the flow of fault current, which can prevent the overcurrent protective device from tripping. This can result in a dangerous voltage being present on the motor frame. Therefore, it is important to minimize the impedance of the grounding path. This can be achieved by using appropriately sized equipment grounding conductors, making tight and secure connections, and minimizing the length of the grounding path. In some cases, it may be necessary to use a dedicated grounding conductor to achieve a low impedance grounding path. A dedicated grounding conductor is a conductor that is specifically installed for the purpose of grounding electrical equipment. It is not used for any other purpose. Dedicated grounding conductors are often used in sensitive electronic equipment to minimize noise and interference. In the case of a motor, the equipment grounding conductor run inside the conduit serves as the dedicated grounding conductor for the motor frame. It provides a low impedance path for fault current to return to the source. The use of nonmetallic Sealtite in this scenario introduces a potential challenge to the grounding system. Since Sealtite is nonmetallic, it cannot serve as a grounding conductor. Therefore, the equipment grounding conductor inside the conduit must be relied upon to provide the necessary grounding path. This underscores the importance of ensuring that the equipment grounding conductor is properly sized and connected at both ends. If the equipment grounding conductor is not properly installed, the grounding system may not be effective, and a dangerous electrical condition could result. To further clarify, let's consider a scenario where the equipment grounding conductor inside the conduit is not properly connected at the motor end. In this case, if a fault occurs, the fault current may not have a clear path back to the source. This could result in a voltage buildup on the motor frame, which could pose a shock hazard. Additionally, the overcurrent protective device may not trip, which could result in damage to the motor or other equipment. Therefore, it is crucial to ensure that the equipment grounding conductor is securely connected to a grounding terminal or lug on the motor frame. The connection should be made in accordance with the NEC requirements and the manufacturer's instructions. Similarly, it is important to ensure that the equipment grounding conductor is properly connected at the MCC end. The equipment grounding conductor should be connected to the grounding busbar, which is connected to the grounding electrode system. The connection should be made in accordance with the NEC requirements and the manufacturer's instructions. In addition to the equipment grounding conductor, other grounding measures may be required in certain situations. For example, if the motor is located in a hazardous location, such as a location where flammable gases or vapors are present, additional grounding measures may be required to minimize the risk of explosion or fire. The NEC provides specific requirements for grounding electrical equipment in hazardous locations. These requirements are designed to ensure that the electrical system is safe and reliable. Furthermore, it's important to consider the role of bonding in the grounding system. Bonding is the process of connecting together all metal parts of the electrical system to create a low impedance path for fault current. Bonding helps to ensure that all metal parts are at the same electrical potential, which minimizes the risk of electrical shock. The NEC provides specific requirements for bonding electrical equipment. These requirements cover various aspects of bonding, including the size and type of bonding conductors, the methods of connecting bonding conductors, and the bonding of specific types of equipment. In the scenario presented, bonding is important to ensure that the rigid metal conduit, the motor frame, and other metal parts of the electrical system are properly connected together. This helps to create a low impedance path for fault current and minimizes the risk of electrical shock. In conclusion, when using non-metallic Sealtite to connect a motor to a rigid metal conduit, a separate grounding jumper wire is not required on the outside of the Sealtite, provided that the ground wire inside the conduit is properly connected at both ends and meets the requirements of the NEC. The ground wire inside the conduit serves as the equipment grounding conductor and provides the necessary path for fault current to return to the source. It is important to consult the NEC and local electrical codes for specific requirements related to grounding electrical equipment. Additionally, it is recommended to consult with a qualified electrician to ensure that the grounding system is properly installed and meets all applicable codes and standards. Grounding and bonding are critical aspects of electrical safety. Proper grounding and bonding practices help to protect against electrical shock, minimize the risk of fire and explosion, and ensure the reliable operation of electrical equipment.